Okay, so we'll talk about hashing. So this problem is which is called a symbol table problem. So this is a very common problem in the compiler design. So basically we have some records, we have n records. Now the question is how we can store the record in a table. So records are typically, say, maybe for a student there are many fields: student roll number, student name, student marks, CGPA, semester wise marks, mark, SGPA, address, and so on. So let X be the pointer corresponding to this record. This is one record. So now, so this one of this field of the record we called as a key of X, which is unique to that record. So we want to store many such a record in a way based on the key value of the record. So this is the problem, how we can maintain a table to have this. So one solution is direct access table. So it is basically an array. Suppose we know that our records are, key value of the records are coming from this set. Suppose this is our, say, some set L, some numbers, this key value can take up to this. So we maintain a table, or basically an array of size L. We can take this T of L. So this is basically a array 0, 1, or maybe this is L minus 1. So L minus 1 is the maximum value of the record, maximum value of the key of a record can take. So now suppose we have a record set where key value is, this is our record set, say 9, 10, 100, 500, like this. So in that case we need to maintain an array of 500, and we put this values. Suppose this is a dot 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 9, so we put a 1 over here, or we can put the pointer of that record, and 10, then we have 100, then we have 500 somewhere here. So this way. So just this is a bit vector. If that key is present, we will put it on, or we will put it off, or we can store the pointer there to access the whole record. So this is what is called direct access table, and remaining values are 0. Now what is the problem with this? Problem with this, suppose our key is just 4 and the key value is huge. I mean, maybe it is, say, till 10 lakhs or something. Then we have to maintain the array up to 10 lakhs. So that is the problem, although we are just dealing with the 5 keys or less number of record. So to avoid this problem, we define a function which is called hash function. So in the hash function we fix the table size. Suppose we fix the table size from 0 to m, 0 to m minus 1. There are m slot in the table, and suppose u is the set of all possible keys. All possible keys. This is the universe of key universe. Universe of key. Then the hash function is a function from this universe to this slot. So it is a function from, it is taking a key and it is mapping to a slot. So suppose this is our universe of the key, and among this is our set of key of our interest, and these are the keys. Suppose there are say n keys k1, k2 like this, and so we apply hash function on it. Suppose h of this is, so h of k1 is say 1 like this, 2 like this. So similarly say h of k2 could be here some say I value. So this is h of k2, and different keys are mapping to this slot, this table into the table. Now the problem is, suppose we have a k5 for which h value is also I. So this is h of k2 and also h of k5, which is also mapping to the same slot. So that means h of k2 is equal to h of k5, which is basically I. Then this situation is called collision. Then this situation is called collision. Now the question is how we can handle the collision, because this is just a slot. So it cannot store two records. So we cannot have two records in a single slot. So this is the problem of hashing when we have a collision, when two keys are mapping to a two or more than two keys are mapping to a same slot, then we have a problem. So how to handle this problem? One way to handling this problem is by chaining. Chaining method to handle the collision. So suppose in the ith slot, this is the ith slot. So k2, k5 are colliding. So what we do? We will put a chain over here, linked list kind of thing. So k2, k5. So this is the way we handle the collision. So whenever a slot is having more than two element, more than one element, so we will put them into the list, linked list. So this is called basically chain. Okay. So now we analyze this chaining method. Okay. So this is our table 0, 1 up to m minus 1, and this is our set of keys of our interest. This is the universe of the key, and suppose n is the number of keys which are mapped here, k1, k2, kn, and m here is the number of slot. Okay. Now suppose we know that our hash function is good in the sense that it is uniformly distributing the keys over this slot. That means if you take any key, it is equally likely to put any of this slot with equal probability. So that is the uniformity of key distribution by the hash function. So we want our hash function should have this property that it should distribute, if you take any key k, and then h of k will be equally likely to be in one of this slot. So that is called uniformity. I mean, that is usually a good hash function. We will see why it is good. So if we assume that our keys are very much equally likely stored into this slot, then while we will search, how much time we are taking to search a key. So basically we need to search a key. So we need to search whether a key is in the table or not. This is one operation we need to do. Another operation we need to do the insert. We need to insert a key. So insert is simple. We will take the key and we will go to that slot, and if it is empty, we will put it there, or if it is already a chain, we will put it into the chain like this. Delete a key, So, we for deletion we need to search that and then we delete from that. So, these two is called dynamic operation. Dynamic operation, because this is insertion and deletion of the record. This is dynamic operation. So, our symbol table should able to handle this. So, we want to maintain we want to have a data structure for our record, set of records. We want to maintain a data structure for our record, so that we can perform this dynamic operation, as well as we want to perform this search operation. We want to search the key whether this is in our record or not. Okay. So, now the question is how we can search a key. So, suppose what we do, we apply the hash function on it. So, we will go to the particular slot, and if the slot is empty, then the key is not there. Otherwise, if the slot is having a chain, we have to search for. So, this is basically 1 plus alpha. So, what is alpha? Alpha is basically n by m. N is the number of keys, m is the number of slot. So, if you assume the uniform distribution of these keys onto the slot, then this is usually the expected number of keys in each slot. So, that is the expected size of the chain, and this is what is called load factor. This is the expected number of keys per slot, or the in other words, it is the expected size of the list chain. Okay. So, when we have to apply a hash function to go to that slot, that is 1, and then to search the key, we have to search in that particular chain in that particular slot. So, that will take the size of the. So, this is the time for a search, and if alpha is order of 1, that means if n is order of m, if the number of slot, if the number of keys in order of number of slot, then this is basically order of 1. Constant time we can get a key, provided our hash function is good hash function in a way that this is uniform distributed, keys are uniformly distributed over the table. Okay. So, now we will come to how we can construct some hash function. So, some construction of hash function we will see. Okay. So, some example of hash function. So, first one is division method. Okay. So, suppose we have our slots are m slots 0, 1, 2 up to m minus 1, and suppose our keys are in integer. So, h of k is simply k mod m. Okay. So, this is the division method. If you take any integer, if you do the mod operation, so this is basically we divide that integer by m, and this is the remainder. So, remainder will be lying from 0 to m minus 1. So, we will go to that slot and we will put it there. So, now the question is how good this hash function is. Well, this will depend on the choice of m. Suppose our k is say 8 bit, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, suppose our m is 2 to the power 3. So 2 to the power 3. So, then m then this mod 2 to the power 3 is basically what? This mod 2 to the power 3 is basically this value, this one. So, whatever value over here, all the, if we choose different values for these bits, then all the values are colliding here. So, there is a huge number of collision, it is not caring of these most significant bits. So, the choice of m in this form is very bad, 2 to the power r is not good choice. So, we will try to avoid to choose m to be 2 to the power r or 10 to the power some power. So, usually for this method we choose m to be a prime number which is not close to, m is a prime number which is not close to 2 to the power r or 10 to the power r for some r. So, that is the, otherwise it will give us huge collision. So, it will not be the uniformly distributing the keys over the slots. Okay. The second method is the multiplication method. So, here instead of division we will take the multiplication. So, this is the second example of hash function. This is called multiplication method. Okay. So, here suppose here we are allowed to choose m is equal to 2 to the power r, and suppose our computers are w bit word. So, we choose h of k, k is w bit, is basically we take a constant, a is a w bit constant, k is w bit, then mod 2 to the power w. So, then if we multiply 2 w bit, it will be 2 w bit, then if we take this mod, it will just give us the w bit, then we will do a right shift of this minus r bit. Okay. So, this will give us a, so we will take an example. Suppose we choose m is equal to 2 to the power 3, which is basically 8, and we choose w is equal to 7. Okay. Now, suppose we choose a constant a to be say 1 0. So, 7 bit 1 1 0 0 1 1 2 3 4 5 6. So, this is our constant a. Now, suppose we choose a k which we want to apply the hash function 1 1 0 1 0 1 1. Suppose this is the k and we want to apply h of k. So, if we have to apply, we have to multiply this. This is the binary multiplication, and if we use the calculator, we will be getting like this. So, this is 1 0 0 1 0 1 0 0. We have to check the bits 1 1 0 0 1 1 1 2 3 4 5 6 7 1 2 3 4 5 6 7. So, this is the multiplication of a and a dot k, and then we have to take the mod 2 to the power w, which is basically give us this part, and then after that we have to take the left shift of w minus r bit. So, w is 7, r is 3, this is r. So, 4 times. So, if we just do the 4 times shifting, then this is our h of k. Okay. So, this is relatively better than the division method, but this involves some multiplication. So, which may take some time. Okay. So, now, so this is this, there are, you can construct some mixture of multiplication and some other way to construct some hash function. Okay. So, now we will talk about open addressing, by which we can avoid the, we can handle the collision. One way of handle the collision is chaining, but for the chaining we need to have a linked list outside the table, but suppose we do not have any memory available outside the table. So, everything we have to do in the table, in the array. So, how we can handle that? We are not allowed to have any extra linked list outside the table. So, that is by the what is called open addressing. So, resolving collision by open addressing method. Okay, so here no extra storage. So, everything we have to do inside the table. So, no extra storage for doing the chaining. So, that means no chaining. So, here what we do? So suppose we have some keys, we want to store it here. So, we will have a probe sequence, we will try. So, first we will apply the hash function, and if it is empty, if it is free, then we will put it there, but if it is not free, then we will do a second attempt and we will apply second say next probe like this. So, this way we will proceed. So, basically we will do like this. So, suppose we want to insert this k is equal to 496 and we have already some numbers over here say. So, 586 133 204 481. Okay. So, the 0th probe, what we do? We apply this 496, this is the 0th probe, and suppose it is hitting here. Okay. So, now there it is a collision, and we are not allowed to have a chain. So, what we do? We will have another attempt. So, we have a sequence of hash function. So, we will choose the second hash function, that is the next probe, and suppose it is giving us this value which is already occupied. Then we have to go for a say third probe, next probe. I mean, so we have a sequence of hash function, we have a family of hash function, and we keep on trying until and unless we get a this free space. So, this is the next probe. So, suppose this is giving us some free slot and we are putting it 496 here, and suppose this is ith slot. Okay. And so, here our hash function is basically, so this is basically we are handling with the sequence of hash function like this. So, it is basically a u cross, this is the probe sequence. So, how many times? At most these times 2, 0, 1 up to n minus 1. So, basically we can denote this by H0 of 496, H1 of 496, H2 of 496. So, we have a sequence of hash function. So, we will try with the first hash function, the original hash function. If there is a collision, we will try with the next. So, this sequence is very important. Okay. Now, how we can search? We have to follow the same sequence while searching, and then we get the key after if we achieve this by this number 2 probes, then we will get the key after this number 2 probes. Okay. but this method is having a difficulty with the deletion. Our table should, our method should handle the dynamic operation like insert and deletion. Insert is this way, but deletion is problem, because if we delete some number over here, suppose if we delete this key, okay. So then when we try to search 496 after deleting this, then what we do? We just go and search. We will just apply 0th probe, it will hit here. We will check whether this is matching or not. This is not matching. Then second probe will hit here, but we see this is deleted. I mean, we do not know whether this is deleted or nobody was there. So we will say no, that this is not in the table, but which is wrong. So we have to have a tag over here that somebody was there, but it got deleted. So then we will go for the next probe and we got the key. Okay, so now we will take some example of the probing. So first one is linear probing. So in linear probing, it is basically we compute h of k plus I mod m. This is linear probing. That means, if this is our table, so we apply h of this first. So this is 0. If I is equal to 0, then it is basically h of k mod m, obviously. Now if this is not if this is not empty, then we have to go for I plus 1 next slot like this. Okay, this way we will keep on search until we get a empty slot. But problem with this method is it will sort of create a cluster in the, whenever a key is there, it will sort of create a cluster below that. So it will not be the uniform distribution of the key over the slot. So to avoid that, we will have a what is called double probing. So this is basically h of k I is basically we have two hash function mod m. So for the 0th probe, it is just h1 of k, that could be our original hash function, because this part is 0. Otherwise, if it is not getting a free, then we have to compute h2 and we have to compute h1 k plus h2 k mod m. If it is still not free, then we have to compute. So we have already computed h1 h2, then we have to keep on try for a free slot by adding this with the h2. Okay. So these two are the example for probing. Now we will analyze the probing strategy or probing method. Analysis of probing. So this analysis, we are claiming that for an unsuccessful search, we need the number of expected number of probes is required. So there is a theorem is telling that for an unsuccessful search, the expected number of probes is 1 by alpha. So how to prove that? Okay, suppose there are n keys and which are occupied into n tables, n slot, our table size is m. Okay, so one probe is required, and so this is the expected number of probe. One probe is required. Now when we go for the second probe, if there is a collision, now when there will be a collision, there are n keys occupied in m slot. So what is the probability of collision? It is basically n by m. So this is the probability of it is hitting a a slot where the number of key, because there are m possibilities, m slot, but we want to hit a slot which is not empty. So, there are n ways we can choose that. Similarly, after that next probe is required with probability n minus 1 by m minus 1, next probe like this. So, this is basically less than equal to 1 plus alpha into 1 plus alpha into 1 plus alpha like this. So, here alpha is the load factor. So, this is basically giving us 1 plus alpha square. So, this is basically 1 by 1 minus alpha. So, expected number of probe is less than equal to 1 by 1 minus alpha. So, if alpha is say 50%, then that means our table is alpha 50% means our table is full halfway. Then this is basically alpha is 0.5 sorry, and then the expected number of probe for an unsuccessful search is 2. Okay. Now, if alpha is 90%, then that means it is 0.9, then 1 by 1 minus alpha is 10. So, 10 probe is required for a unsuccessful search. Thank you.